It is my honor to introduce our second speaker, Ewald, who is a leader and has held many hats in high-performance computing systems and graphics companies. He is currently the president of D-Wave International, the world's first commercial quantum computing company. Prior to this, he was a chairman, CEO, or president of Perceptive Pixel, the touch-sensitive display company, computer graphics pioneer Silicon Graphics, and Cray Research, the first supercomputing company. Bo began his management career at the prestigious Los Alamos National Labs, and he was the head of its computing and communications division. He is involved in various industry organizations and was appointed to the President's Information Technology Advisory Committee by President Clinton and Bush. He has also served on the boards of several public and private companies. For computing students in the audience, Bo had Stan Ulam as advisor and had several interactions with Feynman. So today, he's going to demystify quantum computing for us.
Well, I don't know if we'll go that far, but we'll certainly talk about it. And maybe we'll try to find out which universe we're really operating in. So thanks so much. It's great to be here. My good friend Jeff Harris is one of your trustees. Jeff is in the back of the room, and we talked about a month ago, and he said that you all were doing this, and it might be interesting, though we're not exactly down the line of AI yet, but to learn a little bit about this different technology. So we'll try to take you on kind of a tour or an introduction to quantum computing, and then sort of the way D-Wave has been approaching it. So how many of you have used a quantum computer? How many of you will use a quantum computer in your lifetime? I think you should probably almost all raise your hands, because I think it's going to be part of where we're going. Whether D-Wave is going to be like Univac, who's heard of Univac? They were an early computer company, or whether we're going to be more like IBM or someone and sustain it is yet to be determined. But it's very early days, and it sort of is like, it must have been in 1955 or something in the traditional computing industry. And so, this is an industry that's been building, or ideas that have been building on people whose names you've known. Anybody ever heard of Boltzmann? Yeah, I bet all of you have. Well, he laid some of the foundation for this, and interestingly enough, how many of you heard of his brother, Restricted Boltzmann? So in fact, our machines may be able to be used or mapped onto a quantum version of a restricted Boltzmann approach, and so we'll just look at that a little bit. And who is the most famous Swiss patent clerk ever? Albert Einstein. And of course, he in 1905 postulated, in fact, that light could be photons. We came up kind of with what we today call photonics, photons, and that was part of the idea here behind what we're doing. And then there was another German fellow who, I don't know, maybe he wasn't too confident or something. He was uncertain about things. Who was that? Heisenberg and the uncertainty principle. And then following that, there was another fellow who kept losing his cat. Who was that? Schrodinger. And his cat, was it in the box? Was it not in the box? If it was in the box, was it alive or was it dead? Well, let's open the box and see. And that sort of laid the foundation again for some of the things that we'll actually talk about, even as silly as it would be. And then there was this Hungarian guy in 1932 who wrote a book that sort of formed the mathematical basis of quantum mechanics as we know it today. You know what his name was? John von Neumann. Yeah, isn't that astounding in a way? And his name will come back. And then later on, or about the same time, Einstein said, I don't know about this quantum stuff or some parts of it. This spooky action at a distance, I don't really believe it. And today we call that entanglement. And it's been shown that things can become entangled over distances now of a little over 1 kilometer. The folks at Delft University showed that. So spooky action at a distance, in fact, is something that we use in our computers, though in our case the distances are quite small. So we'll talk about that. And then, along came some world wars and that sort of stuff, and some of the theory behind all this kind of quit for a while, and John von Neumann and others went to Los Alamos during the Manhattan Project, and Richard Feynman was a young student there, and Fermi was there, and all kinds of these brilliant folks were there, and they kind of got to working on other projects for a while. But then as that moved along, and transistors were invented, and then Gordon Moore wrote his famous paper, how long ago? 50 years ago, when he wrote and it was published in a magazine. How many of you have ever read a magazine? They were paper, they were mailed to you, and it first came out in this magazine, and that was 50 years ago. And then for 50 years, we've been building computers that are doing quantum things, but we fight against letting them do the quantum things. Because in traditional computers, quantum things will cause bits to flip from a 0 to a 1. They'll cause current leakage. So we sort of have been building anti-quantum computers. And fortunately for us, there were some young folks, just like yourselves, who 17 years ago had taken, they were PhD physics candidates at the University of British Columbia. And they had taken a class on entrepreneurship and said, let's start a business. Does this sound familiar, Max? And, and we'll get to that part of the story in a second, but it was sort of the same story of let's start a business. What should we do? Quantum stuff. And then what? And then so this is kind of the rest of that story. And which leads us then to Richard Feynman again, who in 1982 said that, it looks like you could build a computer using quantum effects. He postulated that in 1982. And in 1983, I had the good fortune, I was at Los Alamos and was running computing there, and we had a big celebration for the 40th anniversary of Los Alamos, of the Manhattan Project. And as you may not be able to see here, the first speaker, the keynote speaker, was Richard Feynman. And Jeff, you'll notice who was the host. It was our friend Don Kerr. Richard Feynman was the first speaker, and his talk was Tiny Computers Obeying Quantum Mechanical Laws in 1983. And a couple of days later, after this seminar was over, Feynman and Edward Teller and Stan Ulam and Robbie and Hans Bethe and others wanted to see what computing was like at Los Alamos now 40 years later compared to using the calculating machines that they had had during the time. So I'm taking them around, and at the time we were the largest scientific computing facility in the world. We had 5 crays, which is about the equivalent compute power as the phones on this table today. But at the time, it was the largest computing center in the world. And so I'll always remember Feynman standing there, and we were showing them these things, and he said, and I can't do his accent very well, or at all, but he said, young man, someday all of these big Cray computers are going to be replaced by quantum computers. And I said something really remarkable, I'm sure, like, cool, wow, or something like that. So that in 1983 was the first time I, at this talk, had ever heard about them, and here we are now, 30 some years later, and in fact they're starting to be able to maybe do something useful. And I'll use the word probably quite a bit because it is a probabilistic world that we live in. And so basically what our machines are rather than fighting quantum mechanics, we try to take advantage of it. And quantum mechanics, we live in a quantum mechanical world. The computers today that you're using are, the quantum mechanical stuff is going on in there, but we've fought against it for the last 50 or 60 years, and we try to take advantage of it in at least an early or a simple way to do that. And so maybe just a quick reintroduction to the world of computing and sort of how it's different. So the world that we come from or that we're familiar with is one which is a binary world. The bits in the world that we use are a 0 or a 1, and they shouldn't be both. And those bits, if my fingers represented 10 bits, those bits are all independent and unique. And if we're doing something on a transistor and we hit a barrier on a transistor, we have to put more energy in to climb over the barrier. Or if we're doing a search and we're in a valley, we have to do more computing to climb the hill, to look over the side to see what's on the other side. So that's how we face barriers in that world. And in our world, we use the principle of superposition, where we start our quantum bits, or qubits, we'll call them. Our qubits at the start are a 0 or a 1 and both simultaneously. So we use superconducting circuits that we'll show you in a minute, and they're clearly in superposition. And then at the end of the calculation, our qubits settle out to the low energy state for the entire configuration, and they will become a 0 or a 1, and that's what we read out as part of the solution. And then entanglement has been demonstrated on our machines across. I'll show you what our unit cells look like, and these are not physics machines, but we're trying to build actual computers, so when you start trying to measure this stuff on a broad scale, you disrupt the computing and it turns into a big physics experiment. But Google and others have demonstrated entanglement at our unit cell level and then probably across 40 of our qubits or so. It's not that others aren't entangled as well, but that's all that's been measured so far. And the idea behind entanglement is that rather than you remember these 10 unique bits that we had before, if we can cause them to become entangled, then we can make moves in a coordinated way across this landscape that we're going to describe. So ours are clearly using entanglement. And then the last one, and the one when we talk about our architecture in a second, that's probably the easiest to think about is when we hit a barrier, we don't have to put more energy in to climb to the top and look over the side. Rather, we use quantum tunneling, and if there's a lower energy state on the other side of this barrier, this mountain range, if you will, in fact, quantum tunneling will take us to that lower energy state. And so that one is, again, probably going to be the easiest to visualize. And if this works, look at that graphic, look at that. Did you see that, moving to a lower energy state? And the ideas then for all of this, and I'll just hit this real quickly. We'll give you copies of the presentation if you want, but a little bit of the sort of the theoretical background behind this. And by the way, if you have questions as we go along, please ask. We'll try to save a few minutes toward the end as well. But in 1984, David Deutsch took the idea that Fineman had then been talking about for a couple of years and said, you know, maybe you really could build one of these things. And then, and it was a sort of the idea was a universal quantum computer, what was really being espoused, one that could solve many different types of problems. And then Deutsch himself and others started writing algorithms, theoretical algorithms, or maybe the algorithms were real, but it was a theoretical computer they were writing the algorithms for. And the most famous one is Peter Shor's. And that's the one which promises that if you had one of these theoretical universal quantum computers, you could probably factor any arbitrary number. And then what would that let you do? Probably break any and all codes that had ever existed, at least that were encrypted using that sort of a mechanism. So that's either a great thing or a horrible thing, depending which side of the fence you're on. To our knowledge, no one runs Shor's out. It doesn't run on our computer, and to our knowledge, it doesn't run on any others. But that's a thing that you'll read about or hear about most, both the good side and the bad side of these theoretical quantum computers. Nobody can do it yet. So these were sort of, this got a lot of impetus or more thinking behind quantum computing. And then that led to people looking at all kinds of different ways to be able to create qubits or quantum bits. And this is an article that was in Science a couple of months ago, and it's in the packet for your reference, but it shows multiple ways that people have been attacking building qubits. We've been using superconducting circuits. Some folks at the Air Force Research Lab over in Rome are using a different approach. IBM has a little different approach, and et cetera, et cetera. So again, very early days, how to build qubits. And then the way that you connect the qubits is sort of the next question. So it's as in a traditional computer, I'm kind of missing something here, but in a traditional computer, you know, you have the physical devices that you're going to build the machine from, and then you assemble those into gates and into arrays, and then you put those pieces together into an architecture, whether it be a GPU type architecture or a general purpose architecture. In our case, the qubits are the basic thing, that the building block, and then the architecture is how you put them together. And the universal, I'll try this one more time. Nope. Some of those blobs had names on them, and representing different architectural approaches to quantum computing. So one of the blobs, you pick which one, it says topological, and that's an approach that Microsoft is following. That's probably, they're waiting upon the discovery of a non-abelian anion, which is still maybe out there. So that, so that's an approach that's probably 20 years away, if can be. Another of those blobs represents the approach that IBM is taking with a universal or a gate model architecture. IBM has a 5-qubit machine that you can access on the web today. If you get approved for it, you can apply for it and try it. We've done that, and lots of folks have. They say it's probably 10 years or so away from being able to be a product. And then with order of magnitude 50 qubits. And then D-Wave is one of those other blobs there. And what we've done is taken this other approach of an annealing type of an approach, so more an analog type of computer, which was easier to build at the start, but more special purpose, not general purpose. So the ideas for, and this is a couple of slides, this is the IBM press announcement from about a year ago, not quite a year ago, about people being able to access their machine, and they talked about it being available in the next decade. And then Microsoft, this was an article from Science or Nature, Scientific American, about theirs, and theirs, my guess, is probably quite a long ways away. But the point to all this is it's early days here. Early days. Different types of qubits, different types of architectures will enable different types of algorithms to be created and run. And in a second, we'll try to link this back to what does all this have to do with artificial intelligence or machine learning. The answer is, so far, not much, but I think the promise is there. So maybe now switching a little bit to D-Wave itself and this first type of quantum computer that's out there. The ideas go back in the late 90s. Some folks in Tokyo Institute of Technology and another group in Europe, and then Eddie Farhi and folks at MIT sort of said, if you could build certain types of qubits, maybe you could hook them together and actually build an annealing type of quantum computer. And so these were the ideas that came along. This is Farhi's paper, and there was another one from some folks at Jülich in Germany and Delft, and as an approach to be able to start working on quantum computing. And this was about the same time that these two young PhD physics graduate students were taking this entrepreneurship class. And they said, let's start a business. And that was a business that became D-Wave. And first they said, okay, we've got a business going, what should we do? This will sound real familiar. Let's write some patents and aggregate some patents, and we'll become rich doing that. Well, I've had and been in other really big businesses where we thought we had huge value in our patent portfolio and we were sure of it, and sometimes you do, but not always. So after a few years, they said, okay, well, that was a great idea, but now let's see what else we can do with some of this IP we have. And at about the same time, this is one of those serendipitous things, I suppose, that happened, was that the US government had been investing and having TRW and later Northrop Grumman building superconducting circuits for them. And TRW decided they were kind of at the end of that road and they were getting acquired, and so they got rid of the group who was building these superconducting circuits. And the superconducting circuit people met these two other guys, and they said, we think we could build a quantum computer, but we don't know how. And the TRW guys said, well, we know how to build what we think could be qubits. Let's try to work together and see. And so that, in fact, then, after a few years, led to them starting to work toward seeing if they could build a quantum computer. And in fact, after a while, they were able to. And the machines have been available for about 5 or 6 years. Lockheed Martin was the first customer. They bought a system that had 128 qubits to start. They've upgraded to 500 and 1,000, and we're now up to 2,000 qubit machines, and I think they'll probably upgrade it to 2,000 in the next year or so. And their application is basically seeing software validation and verification, but doing it in a different way. Instead of trying to prove program correctness, that all of the sensors and controls and things on an aircraft all work together, the computers and the networks all work together. In a traditional computer, you have inputs, and then you have a simulation, and then you get answers out. And that's how it runs. Inputs run the program, you get answers. Well, with our machine, if you know any two of those three big chunks, you can kind of figure out the third. So what Lockheed said was, if we could create a simulation of this aircraft and systems and controls, and we'll give it a bad answer and run the D-Wave machine backwards, let's see if there are any inputs. which then would have caused this bad answer. So as an answer, they would have said, okay, pilot pulls back on the stick and the airplane goes down. Very bad. And so let's postulate that bad answer, that anomalous answer, and run the program backwards and see if there are any inputs which would have caused that bad answer. And in fact, in doing that, after a short period of time, they demonstrated that they benchmarked it against problems they'd had on fighter aircraft and found some of the same problems in a short period of time that it had taken them 6 months, I think, to find using the older tried and true mechanism they had. So that gave them heart and hope. And that machine is actually at the University of Southern California. It's housed there, and USC runs it for themselves and Lockheed, and they each have about half of it. USC does sort of performance characterization, optimization work, and physics characterizations. Google became the second customer, and they bought their first machine about 3.5 years ago. It had 500 qubits. They upgraded it to 1,000 qubits, and we haven't announced this yet, so I'd ask you to not do that, but they're headed for 2,000 qubits here shortly. And then Los Alamos National Lab became our third customer a little over a year ago with a 1,000 qubit machine. And then our fourth customer we just announced is a small company called Temporal Defense Systems, working on cybersecurity problems for unnamed people. And so that's this little business. These are supercomputer class machines. They sell for about $10 million each. Of course, you can lease them if you want to break those payments into yearly or monthly payments. We're glad to talk to you about that. But they're supercomputer class machines. And the way they work is, or at least a way to think about how they work, is if you have a problem that you can map onto an energy landscape, I love the way you use your hands. So if you have a problem you can map onto an energy landscape, what this machine does is natively or naturally, it syncs to its lowest energy solution, and it finds the lowest valley or valleys in that energy landscape, probably. It's also probabilistic, so it's not guaranteed that you're getting the best answer. So you don't run it once. It's not a deterministic machine. You run it many times and get a sampling of answers or a distribution of answers back, which again is going to come back to sound like some of the things that some of you do. Sir?
Very quick question. Is an annealing schedule required?
There is an annealing schedule, exactly. So which at the start, so maybe a word about annealing. So basically what we do with this machine is that we'll set it up in a superposition state, and you give basically weights for the qubits and the strengths of interactions between qubits. And in doing that, you can build this landscape. And then we go through an annealing cycle where we excite it a little bit and then let it settle out into a low energy state. And that's like annealing at the low energy state then is where the metal, if you were doing real annealing, the metal has hardened. So we let it harden, and then we read out what the qubits are. And then we go through that cycle again and again and again. And we can do 5,000 to 10,000 of those complete cycles a second. And each time it goes through one of those cycles, it doesn't add a number, it doesn't subtract, but it rather seeks this low energy solution and ends up in that low energy solution. And it searches through a potential solution space of 2 to the however many qubits you have. So we now have systems that have 2,000 qubits, so we're searching a potential solution space of 2 to the 2,000th. That's a pretty big number. And, and it's kind of a sparse set of solutions typically, but that's what it's doing. It's really looking through this huge solution set, and then it will give you a sample of answers back. And so and it's also dependent on the problem. So if the problem that you have, the energy landscape, is like the Alps, so very steep, skinny mountain ranges, and somewhere at Interlaken, a low valley or something, and you run it 100 times, you might get 91 of the answers will be at Interlaken, and then some will be a couple of other places, and there'll be some crazy ones. But if the energy landscape is the Sahara Desert, which is flat, where the highest elevation is a grain of sand, you're going to get answers all over the place. So again, quite different than the deterministic world that we've come from. But that's the way to think about the way this machine works. And so the little challenge is, it's real simple to use. There's one instruction. So it's you know, this is a really, really, really reduced instruction set computer. It's also a very, very, very long instruction word computer, because in that one instruction you give all of the values to specify your problem. But the little challenge is, how do you map real world problems into this sort of a thing? And so what it looks like it's good for is certain classes of optimization problems, maybe machine learning that Google and we are doing a little bit of work on, and then Monte Carlo or sampling sorts of applications. And so just quickly, what it's not is, it's not like anything you've ever done before, unless you grew up in the 40s and did programmed analog computers. That would be the 1940s, not the 1840s. And here is a traditional Intel 64-bit processor, and over on the far right is ours. We don't do any floating point operations, so we do 0 flops. And the precision is 4 or 5 bits. So when you're specifying this energy landscape, there's not a lot of dimensionality to it, which is a challenge today. And we do about 10,000 instructions a second, but each of those instructions solves this complicated energy landscape. And there is only, you know, not 500 instructions. You have to learn this one. It's really easy to learn, but the challenge, again, is putting stuff onto it. The machine runs at near absolute zero, as we'll see in a second. And it's really a chip. I'll show you the chip in just a second. And it's superconducting, consumes no electricity virtually. We're up to about 2,000 qubits today. And it really must be like it was in the 1950s or something like that in traditional computing. It's very early days, and it's a place for pioneers. But if you get an algorithm to run, you'll probably be the first person in the world to ever have run on a quantum computer, to run that algorithm on a quantum computer. So just a couple of things. I'm going to show you 2 things real quickly, and these are from Google. So these are now 3.5 years ago. So Google gave us a set of benchmarks. These are random optimization benchmarks that they wanted us to run and to see how our machine would do. And so this is a timing chart. So going down is better. Down the chart is better. And the problems range from very small up to larger, as measured in qubits here. And so these are discrete combinatorial optimization benchmarks, and they had us run them, and then they ran them on IBM Cplex and Taboo and some other optimization software. And the D-wave line is the red line, and it's sort of uncharacteristic to what we're used to, in that no matter the problem size, it does about 5 to 10,000 instructions a second. So it's flat, no matter the problem size. And the other lines are more characteristic of what we've seen in high-performance computing for many years. And for the smaller problems, the D-wave machine was a factor of 100 slower, but as the problems got larger, it was about 10,000 times faster. And Google said, oh, wow, maybe if we could, this is no guarantee of success, but if we could map problems onto it, there at least is the potential that it might be able to perform. And then secondly, they said, okay, let's now see if we can teach the thing to be able to recognize a car out of this set of training images. So they and we worked on this for 6 months to turn this optimization engine into something that could classify cars. And it turned out that at the end of that 6 months, by about 6 people, so a lot of work by hand, in fact, the D-wave machine was able to recognize cars correctly out of this set of training images about 94% of the time, compared to 84% of the algorithm they were comparing us to on the traditional machine, which was great. But more importantly for them was when they took the classifiers from the D-wave machine and put them back on the traditional machines, it only used about 1/3 of the CPU cycles. And what was driving the program at the time was Google Glass, who have a battery-operated computer, and if you can save 2/3 of the CPU cycles, that's the big thing. So that was actually more interesting to them than getting a little better at it. So they said, gee, it looks like it might have performance potential, and then secondly, with a lot of work, it looks like we can map a machine learning problem onto it, and so it has promise, and so let's get going and see if it could work. And so that led them to get it. And then as they learned more about it, so this is now a result from a year and a couple of months ago, they said, you know, let's look at another problem and put it on the D-Wave machine, and this one is a really rugged energy landscape. And they ran that against simulated annealing, which is same sort of approach running on a traditional computer, simulating what the D-Wave would do. And that one turned out to be about 100 million times faster. It's a really little corner case. It's not a fair comparison. It's all of those things. But you should read the paper because, again, it gave them, I think, more heart that at least the direction that we're going, at some point, if it becomes a little more generalized, there is performance potential. That's a pretty big number, too. And the way that we've been able to move forward is that in rough numbers, so this isn't Moore's law, but it's going to sound pretty familiar, where every 18 to 24 months, we've roughly been able to double the number of qubits. So from 128 qubits, which was the first commercial machine, to 512, 1,000, and now 2,000 qubit machines are out there. And we expect, you know, in 2 or 3 years from now to probably have a 4,000 or 5,000 qubit machine, and then there's a path to about 10,000, sort of in the same packaging. So looking beyond that then, this is actually 2 D-Wave machines. The new one is called a 2000Q, and the machine itself is a chip, but it comes in this big box, which has some racks in front. And the racks are cooling and equipment to interface it to the outside world. If you open that big box, which is about 10 feet by 10 feet by 10 feet high, it's mostly open space. And it's big enough so that in these early days, you can have 3 people in there at the same time working on the machine. And if you opened the door and stepped in, you'd see this big can that's about that tall and about that big around. And inside that big canister are other canisters, and you take them off one by one. It's sort of like the Russian dolls that stack one inside the other. And inside each of those layers, each of those containers is a gold disk that they connect to, and you can see the temperature going down. And so this isn't the Terminator brain, but rather like the Terminator arm, is what some people have called it. And you can see where it gets colder as we go down. So it's actually in that big box, it's room temperature inside, and then liquid nitrogen temperature at the top of the Terminator arm. And then we're running at about 12 to 15 millikelvin at the bottom where the processor is. It's probably the coldest, at least the coldest known spot in the universe. And sometimes we get into debates about negative temperature and stuff, which, you know, may or may not exist, but for the known universe, it's pretty cool. And we've done a lot of work in trying to make them reliable, and in fact, we have systems in the field that have run now for about 22 months without failure running at that temperature. We have some maintenance that we do on them from time to time. Again, consumes no power since it's superconducting. And that is the quantum computer. It's a chip. It's the size of your thumbnail, and this one is what the next picture is, even breaks that down. If you look at this picture, you would see can you see little squares on the chip itself? So it's about the size of your thumbnail, and then we build it like we do in other parts of the computing industry by creating unit cells and replicating those side by side. So in this case, there's an array of 16 by 16 by 8, which if we multiply all that together should give some number you've heard of before. But each of those unit cells looks like this. So we've taken one of them apart, and in red are the qubits. And the qubits are really superconducting circuits made of niobium. And there are, in this picture, 4 horizontal ones and 4 vertical ones. We've outlined 2 of them. And so for each of those qubits to program it, you give a weight or sort of a value to the qubit, and then you can specify the strengths of the interactions between qubits. There are couplers between the qubits. So a qubit can have an influence on its nearest neighbors, more or less, and then also on the adjacent qubits off cell. So that's how you program it today. One of the big challenges with it is the connectivity is not general or broad enough for big problems, but you can at least start using it to create this energy landscape and then be able to solve it. So that's, you know, at the core, that's what it looks like. We build these chips in a Cypress semiconductor plant in Minneapolis, and put them together into the system and, and ship them out. So we've figured out how to do this work. And we do a little bit in our offices in Palo Alto of the fab work as well. But that's sort of the nuts and bolts of it. And the programming environment, this is a fancy chart, but the reality is it's more chart than software. So, and big hat, no cattle is sort of a part of this. I live in Montana, by the way, and that's an appropriate saying for there, I suppose. So at the bottom are chips, and at the top, are what you would hope for at some time are applications, but those don't exist yet. And so we've been building the software environment in a way that will look familiar to you. We've been trying to do prototype software, figure out what works. And at the start, you program it at the machine language level, at this SAPI level, and then we created libraries in C, C++, MATLAB, and Python to let you more easily do that and dispatch programs and get them scheduled and run and come back. And then borrowing from what we've done in traditional computing, we said, okay, maybe rather than having to think about the machine on its terms, let's create an intermediate representation of a problem to map onto it, and that's a QUBO, quadratic unconstrained binary optimization form that I think many of you on the computer science side would know. And then the problems you want to solve are actually a lot bigger than the machine, so we said, well, let's create sort of a virtual QUBO that can be a lot bigger than the physical machine, solve it in chunks and glue it back together. And so we've run problems that are about 20 times larger than the physical machine now, starting with this virtualization approach. And so we've run problems that are order of magnitude 40, would have consumed 40,000 qubits worth. And then we've started doing some prototype software. I won't bore you with that, but little prototype tools that are specialized towards subject matter experts for optimization, constraint satisfaction, and there will be others. And then Los Alamos has written a macro assembler. There's a startup company called 1Qubit that's created an environment for the machine. So there's starting to be an ecosystem around software. Just this week in Washington was a seminar, quantum software testbed workshop or something like that. And there were 3 days, and people from all around the world came and gave talks about this building software environment. So it's great. And then still looking for, there's no compiler yet, but if we ever had one, I would call it Quartran. You can tell where I started, or Q++ or something, and you'll see these are all just fictitious make-believe things, but someday there will be those. And then real applications that run on it. We just open sourced our QBSolve, that intermediate representation software, and got good coverage and good reception from it. And so that was a cute headline about it. This is the way that you actually program it, is that you specify the weights of the qubit and the strengths of the interactions between them. It's the representation of what the machine is doing is the Hamiltonian that's at the bottom, and that's what you think it's solving. It's doing something close to that, but that's really what you're programming. And this isn't my speechwriter, but to show you how easy it's become to use, this is Scott Paikin, who's the technical project leader at Los Alamos. This is his daughter, Sophia, who we believe was the first person to ever program a quantum computer before a traditional computer. And so he was fiddling with it at home, and she became interested in it, and he showed her how to do it and sort of how the machine works. And her first program was to take her class, these qubits, each qubit was a classmate, and then did this classmate get along well with this one or not, and this one, and that sort of thing. So I think what she really did was separate her class into kids she liked and kids she didn't like. But that's the first 5-year-old program that we know of on our machine. And then lastly, just potential applications here. And so I'm going to take you on a little tour. These are, again, we'll leave you with this, but you can look up these papers. This was from Lockheed, and so now I've targeted most of these toward machine learning. So early days, prototype stuff, but at least pointing the way that there will be some applications here. So Steve Adachi and Henderson of Lockheed Martin, application of quantum annealing to training of deep neural networks. I won't bore you with that, but that was one. And then a fellow Alejandro Perdomo Ortiz, who's now at NASA Ames, gave a talk at our first ever users group conference about quantum assisted algorithm for sampling. And these are, and again, you'll have access to all of this stuff. And said, it's hard to do, but there's potential to it. And what you'll see in some of these, in fact, is that the way the machine, the way the qubits are coupled together, you can make it look like a restricted Boltzmann machine. And so you can get a quantum Boltzmann sampling back from it and then go off to use it in your problems. So this was another one from folks at Los Alamos, Boltzmann sampler, restricted really. And then here was another one from Los Alamos. And these are from our users group, and I've included this because there are a couple of websites here that have presentations that you might be interested in looking at, the one at the bottom here. And these are some of the Los Alamos, when they got the machine, they said, if you want to try to run on the D-Wave machine, we'll give you some time and you can take some of your own time at work to run on it and see, and see what happens. Try it and see what happens. So they had about 10 rapid response projects that are at that website. And the idea was let's see how well the machine would work. And holy cow. That's a different color than it started. But hopefully you'll be able to read it in there and you can go to some of those papers and see what they're like. But these were some of the, again, I won't read these to you, but these were some of the conclusions that they came to. And of the first 10 or so projects they tried, I was shocked. About half of them found results that were sort of in the same order of magnitude as on conventional computing. And there was one of them that came up with a little better results than on a conventional computer. So this was their right out of the bat, the first things they ran on it. About half of them at least showed promise, and of those, one or two of them showed like there might be real promise. And they ranged from a signal processing application on the bottom of this, optimization at the top. This one was wild, graph partitioning for electronic structure problems. And in fact, they found that the D-Wave machine was comparable to existing methods and sometimes better after this initial thing. And then this was another one. I loved this one, of course. And this was a fellow who really started off as kind of a skeptic and looked at optimization problems. And in the end, he drank the D-Wave Kool-Aid, and this was his chart with the heart around D-Wave. And so we felt, we made progress starting from sort of scratch here. Again, very early days, lots of work to do, but if you like to do things that are both at the cutting edge of your world and the cutting edge of what will be computing of tomorrow, this is a place to do it. And more than anything, we need a couple of sets of things. We need more smart people thinking about applications, and then we need another set of smart people thinking about how do you create software tools to be able to let this thing run. So with that, I may have a couple of minutes, but thanks for your attention. I'll be here all day, and so really appreciate it. And I forgot to show you this at the start. I have a new shirt because I've been on the road for 2 weeks, and so all my other clothes are dirty. So I bought a new shirt, and this is like the coolest shirt I've ever owned. I'm not very stylish, as you can tell. This shirt is not a button-down collar, but this is a button-up collar. Look at that. Isn't that cool? Who would have ever thought you needed buttons underneath your collar? And the reason I bring that up is it makes the collar horrible to try to attach the microphone to. So I'll never wear my button-up collar shirt for another talk like this.
Thank you for a very engaging talk, Bo. Now we have a few moments for questions from the audience.
Excellent talk, and I like the idea of Q++, by the way, so I'll be the first one to use. My main question is, in the early days of parallel computing, we built machines, especially in those government labs, say 1,000-core computers. It was the biggest thing ever. What they did those days, they had done the interfaces and made at least the to submit their problems or model their problems and run them in those, which basically let them solve the problems. So my main question to you is, looks like you have a machine which is doing something phenomenal, but it's not available for everyone. Everyone is not Google. Certainly academicians don't have that type of resources. My question is, as you have these software being developed around your machine, and as you made your code open source, which is great, when or is there a plan to make your machine to be available to the academicians or professionals which have really hard problems, but they don't have any hardware to run on? And if that's a possibility, that will speed up the process of making this quantum computing actually leap for more than doubling up every year.
Yeah, so I agree completely. We would love to be able to do that. That was probably my neck or something rather than this thing. We would love to be able to do that. We're trying to turn this into a business, which means you need to sell computers and make some money. So let's talk to our friends, whether they be at Air Force Research Lab in Rome or DARPA or wherever, and figure out a way to at least get part of one funded and put out somewhere. You know, and if that doesn't happen seriously during this year, then I'm going to find a way to put one out there. Because, you know, I mean, you saw the results of Los Alamos really using it for 3 months, and we need thousands and thousands of really smart people trying it. So we'll figure out a way to do that. And I would envision, you know, then we'll have student contests and one thing and another, and, you know, at some point get round to like the Bell Prizes and those sorts of things.
Just very quickly catch up what you just said. I really like your example of Sophie, the 5-year-old, and I think it's also a good tool to think about teaching problem formulation.
Exactly.
Not just quantum computing programming, but also problem formulation. So I'm wondering that whether you have any interest to work with RIT, to kind of build some collaboration tools, education tools, not for college students or K through 12, about that problem formulation.
Yeah, exactly. We would love to do that. And in fact, we yesterday had a great session with the DERSIG people to talk a little bit about what we're doing and what they're doing. So would love to come back at some point and maybe bring our fellow who wrote some of those tools that Sophie used, and we can talk about that. Because again, you know, I would like to focus things on 2 or 3 or 4 projects, some on software tools and some on applications, and then figure out a way to get going. So absolutely, we'll be back.
Thank you. Santosh.
Talking about very efficient computing using quantum computing, but where does the memory reside?
Yeah, so this is different, you know. There's not really a memory. So you formulate, we're like early days of memoryless GPUs. Even cashless GPUs is the way to think about it. And basically you create your problem on a host machine somewhere, and then you send us over the strength or the values of those qubits and the interaction strengths between the qubits. And then we solve that problem, and you'll tell us how many times you want it solved, like 100, and then we'll give you 100 of the results back. So there are buffers on it and things, but it's really, it's in a way, it's almost like maybe an active memory itself, in that you program it, and then it solves the problem that you've programmed onto it, and then you read the results of the memory back. But it's, you know, it's a different animal. I don't even know if we should call it a computer. You know, it's doing something, but it really is quite this different animal. So maybe with that, I think we're out of time. So let me just say one other thing and sort of follow on what Max said earlier, and that is that, you know, as you all go forward through your careers, and you're going to create software and deep learning models and programs that are going to do things that you and I aren't going to know how they got to that conclusion. So with that sort of freedom and the ability to do those great things, there's also responsibility. And I'm going to just go back to, you know, make up a mythical car company, like a big one in Germany that has 2 initials, WeV or something. And, you know, imagine that you're there 10 years ago or something, and you're the big shot business person, and you say, you know, we've got this new line of diesel cars coming out. And, you know, the people who've been testing them, the emission results aren't going to pass the U.S. standards. I don't know what the problem is. We need to fix the problem. And so they call in the software people who've been, creating the software that drives that operates the engine and reports the results back, and say, we got this problem. Can you guys fix the problem? And they say, well, I don't know. We can fix anything with software. Let's think about it. And they come back the next day and say, yeah, we can fix the problem. And the business people say, great, go fix the problem. We got that emission problem solved, and the software guys don't exactly talk to the business guys, and they probably don't say, well, by fixing it, we're going to fix it. You're going to get numbers you like, but we fixed it. And the business people, who knows what really happened, but the business people didn't maybe really say, well, how did you fix the problem? Did you really, did we make the engine more efficient? Did you tune the software so we made the engine more efficient? Here's a silly case, and we're going to see how this plays out over the next few months. But, you're going to have even more responsibility in your world to be able to explain what you're doing and do critical thinking about what's happening as it gets applied in business or as it gets applied in medicine or other areas. So we're going to end up with these great, unbelievable, fantastic things that you can do, but behind them, we need to have at least some idea that what they're doing is right. And when you fix a problem, that you've really fixed the problem. So with that, would say again, thank you, and really appreciate the invitation, and thanks.
Thank you both. Oh, super.